Hello, algebra students. This is an interesting but also complex lesson on section 4.5, which is about solving quadratic equations by finding square roots. But before we dive into that, we're actually going to spend most of our time talking about something slightly different, which would be how to simplify square roots. So let's dive into what it means to simplify square roots. In order for a radical, what I mean by a radical is this symbol here that you guys are used to. I'm not calling it a square root because in the future we're going to be learning about other types of roots, third roots or fourth roots, not just square roots. So this is going to apply to any root. In order for a radical to be simplified, make sure there are no radicals in the denominator. Okay, that should be pretty straightforward. We should never have a fraction with a square root sign in our denominator. If that ever is the case, it's going to be wrong and incorrect. We can also have no perfect square factors underneath our radical. So within your radical, you cannot have any perfect square factors. I'm going to really dive into that here in a second. We can also have no fractions underneath our radical. So I can never have a radical sign with a fraction here. This, for example, would be an incorrect answer. We would have to actually go ahead and simplify that. So what does this mean? There are no perfect square factors underneath our radical. Well, the perfect square factors, and you guys are going to want to write this down big, highlight it. It's going to be referred back to a lot. The perfect square factors would be things like 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and then we could go 225 if we want to too. These are all the perfect square factors up until 15 squared. Okay, where do they come from? Well, hopefully you picked up on the pattern. This is 1 squared, and 2 squared, and 3 squared, and 4 squared, and so on and so forth. Okay. What option number 2 or rule number 2 states is that none of these, other than 1, because 1 is trivial, none of these numbers can be factors underneath our radical. So we're going to have some number underneath our radical sign. I know the next example is, I believe, square root of 27. Yikes. Square root of 27. This is not a simplified radical or square root sign because it has some, or at least one, of these numbers as factors of 27. Which number in this list is a factor of 27? Well, it would be 9. Right? 9 times something is 27. And so that tells you that it's not simplified. Okay, because one of these numbers in this list is a factor of 27. If it was a larger number, something like the square root of 405, the way that you would do this is you could just start, and this list gets bigger too, but you could just start with 225, for example. If you do 405 divided by 225, it won't come up as a nice number, as an integer. So then it's not a factor. You do 405 divided by 196, 405 divided by 169, and see if any of these numbers are factors. And the number that is a factor of 405 is 81. Okay, because 81 times 5 is 405. So that is the process for identifying if something is has a perfect square factor. And we'll talk about how to simplify that in a second. We're going to use these two properties to simplify our roots. Let's say that we had the square root of 27, which we're going to have in the next slide, I know. But anyway, we'll do it now. The square root of 27. I know that 27 is the same as root 9 times root 3, right? I can do this with any factor. Let's say I had the square root of 24. This is the same as the square root of 8 times the square root of 3, or the square root of 4 times the square root of 6, or the square root of 2 times the square root of 12. If you type in root 24 in your calculator and push enter, you're going to get some weird decimal. If you type in root 8 times root 3 in your calculator and push enter, you're going to get the same decimal as any of these. Okay, as long as the two numbers multiply to that number, we're going to be okay. That is a legal simplification. This one here, the quotient property, just says if you have the square root of a fraction, that's the same as the square root of 1 over the square root of 2, the square root of the numerator over the square root of the denominator. So one of my rules, rule number 3, said I'm not allowed to have any fractions underneath my square root sign. This is the way we're going to fix that. We're just going to take the root of the numerator and then the root of the denominator. However, we robbed Peter to pay Paul here. Okay, we fixed one issue, but we created another because the first rule said that there cannot be any roots underneath our denominator or in our denominator. So we're going to have to fix that as well, but that is going to be the first step. When you have a fraction underneath your root, you're going to take the root of the numerator, divide that by the root of the denominator. All right, square root of 27, as promised. This one doesn't have any fractions, so I know that the only issue that it's going to have, the reason why it's not simplified, is only going to be because of the rule number 2, which said I can't have any perfect square factors of that number. We listed out the perfect square factors. You guys should have that as a reference to your notes right now and be referencing that throughout this lecture. So I have the square root of 27. 27 has a perfect square factor. One of those numbers on that list is a factor of the number 27, and you guys have already established this, that it's 9. And by the product property, we said that the square root of 27 is the same as the square root of 9 times the square root of 3. And because we are brilliant mathematicians, we know that the square root of 9 is 3. So the square root of 9 becomes 3. The root 3 can't be simplified because if I go back to my list of perfect square factors, it goes 1, and I already told you 1 is trivial, meaning it doesn't actually do anything. I know that 1 is a factor of every number, so disregard 1. 4 is not a factor of 3, right? So root 3 is a simplified root versus root 27 isn't, because root 27 had 9 as its factor. So the square root of 27 simplifies to root 9, root 3, and we know what the square root of 9 is. It's 3. Class, it should be intuitive, or it should make sense to you, that if you were to take the square root of, here's my list, if you were to take the square root of any of these numbers, it's going to come out as a nice number. It's going to be simplifiable, right? Square root of 4 is 2, square root of 9 is 3, square root of 16 is 4, square root of 25 is 5. That's the reason why all these numbers are listed here. So if you take one of those numbers out as a factor, you will always be able to take the square root of it and get a nice number. And so this is the answer to simplifying the square root of 27. It's just 3 root 3. You should be able to right now take out your calculator and type in the square root of 27 and get a decimal. And then you should also be able to type in 3 root 3 and get that same exact irrational number, that same exact decimal. Once you try this one, look at your list, try to identify any perfect square factors. If you don't know, you're just going to take 98 and you're going to start with a number smaller than on its list and do 98 divided by that number. And then do 98 divided by the next number. You want to pick the biggest factor if there are more than one. So the square root of 98, hopefully you guys identified that 49 is a factor of 98. 49 times what? 49 times 2. So the square root of 98 is the same as the square root of 49 times the square root of 2. Guess what? We know what the square root of 49 is. That's why we picked that number in the first place. The square root of 49 is 7. So we would end up with 7 root 2. Let's carry on. Root 10 doesn't have any perfect square factors. Okay? The only numbers that are smaller than 10 are 4 and 9, and neither of those numbers can multiply to 10. Very same thing with 15. But our product property says that I can multiply these things, and it will be the square root of 150. And now I'm going to look at the number 150 and decide if that has any perfect square factors. Does it? The answer is yes. Okay. 25 is a factor of 150. And 25 is a perfect square. So the square root of 150 would break up as root 25, root 6, And of course, because 25 is one of those numbers, I can actually take the square root of it, and it'll be 5 root 6. Carrying on, this is going to be almost the same. I'm going to go ahead and do 45 times 2. That's 90 times 3 would be the square root of 270. This one should be relatively simple because we know that 27 is a perfect square factor. And this would break up then as the square root of 27 times the square root of 10. Just kidding. I don't like that. 27 isn't one of those numbers, right? It has perfect square factors, but it's not one of those numbers. So let's not do that. 270 is divisible by 9. So this would be square root of 270 is the same as the square root of 9 times the square root of 30. And 9 is one of those numbers. 9 would be 3 root 30. But then we have to look at 30 and make sure that that number doesn't have any perfect square factors. And it doesn't look to me like it does, right? The factors of 30 would be 1 and 30, 2 and 15, 3 and 10, and 5 and 6. None of these numbers are perfect squares. So then 3 root 30 would be simplified. Let's talk about adding and subtracting square roots for a second. This was all multiplication and division so far. Okay, all the examples that we looked at. In order to add or subtract square roots, the number underneath the square root must match 100%. I cannot add the square root of 5 plus the square root of 6. That's a big no. We can't do anything with that. That is simplified. In order to add numbers, the square roots must match completely. I could add square root of 5 plus the square root of 5, for example. I don't think it would be what you think it is, though. I think a lot of people would try to do like square root of 10 or something like that. However, the actual way that you add these is you add or subtract the coefficients and leave the numbers underneath the radical the same. So this root 5, it's really saying that you have 1 square root of 5. And this is, you're adding 1 more square root of 5. So just like if we have x, you can put a 1 in front of it. If there's no number in front of square root of 5, you can put a 1 in front of it. And then when you add these, it's like you have 1 root 5, and you add another root 5. How many root 5s do you have now? You have 2 root 5s. Okay, so what you're doing is you're adding the coefficients, the numbers in front, but you're leaving the roots the same. That's why they have to match. These don't match. You couldn't ever add them. So, problems like this will probably be pretty simple then. 2 root 15s plus 3 root 15s, you would take the coefficients and you could add those and you would have 5 root 15s, right? The root is staying the exact same, but you're adding or subtracting the coefficients. Should be able to look at this one and come up with the right answer. Notice that this one has a different number underneath the root than these two. So this one is going to be off on its own. It's not going to be able to be combined with anything because its root doesn't match. But these ones do have the same root, so you're going to add or subtract the coefficients. 2 minus 3 would be negative 1, and the root stays the same. It would be 3 root 2 minus 1 root 3, or this could also be written as, I would mark that right, but it could also be written as that. Right, we don't need the 1 in front. All right, so it's not always going to be that same level of difficulty. We are going to have problems where I throw at you different roots, numbers underneath the root, and the answer isn't just it can't be simplified. There is a simplification that can happen here. What we need to do is we need to combine the first thing that we looked at with this example. First, look to try to simplify your roots. Root 15 is already simplified, so that's just going to be 2 root 15. However, root 60 does have a perfect square factor. Go back to that list, right? You're going to need that list if you haven't figured this out yet. You're going to want it on your note card. You're going to want it in an easy, accessible place in your notes. Because square root of 60 does have a perfect square factor. It's 4, right? and 4 times 15 is 60. So this is going to break up as root 4, root 15. Now we know what the square root of 4 is. The square root of 4 is 2. So we're going to have 3 times 2 root 15. And we can do this multiplication. We can do 3 times 2. That's 6. So we have 2 root 15 minus, do this multiplication, 6 root 15. I can add or subtract my coefficients, leaving my root the same, and come up with negative 4 square root of 15. I do want to emphasize something here. All of these should be able to be checked very simply. You should be able to do 2 root 15 minus 3 root 60 and get that decimal. And then make sure that this is the exact same. Make sure that negative 4 root 15 is the same decimal. Okay, so we have negative root 32, and 32 does have perfect square factors. If you look at that list, 16 is the biggest factor of 32. That's a perfect square, and it would be 16 times 2. And if you're looking at the number 200, that would be 100 is the biggest perfect square factor. So it would be root 100, root 2. Now I can actually take my perfect square, my square roots of perfect squares, right? Root 16 would be negative 4 root 2. And the square root of 100 is 10. So 2 times 10 would be 20 root 2. We can add or subtract the coefficients here. Negative 4 plus 20 would be 16 root 2, final answer. This looks disgusting. Why don't you go ahead and try this? Pause it here, give it a go, simplify each one individually, and then move on from there. You will, just to emphasize this, you do have a question like this on your quiz. It's not too bad. Just go one by one. This one is simplified. That's just negative 3 root 5. 112, I'm not seeing the perfect square factor. I'm just going to kind of skip over that until I grab my calculator. This one would be 4 square root of 27. We already did simplify that. We know that 27 is the same as root 9, and then 9 is its perfect square factor, and 9 times 3 is 27. This one also has 9 as a perfect square factor, so it would be root 9 times root 5. And then, like I said, I don't see the root of 112 right now, so I'm just going to take my calculator and do 112, and I'm going to start dividing it by those perfect square factors. So I'm confident that 64 isn't a factor, so I'm going to go underneath 64. 1 underneath 64 would be 49, and 112 divided by 49 is 0.02. It doesn't work. So 112 divided by 49 is 36. No, doesn't work. 112 divided by 25 obviously doesn't work. What about 16? 16 did work. So when I divided by 16, I got 7. So this is going to break up as root 16, root 7. Now I'm going to simplify all the ones that I can. This one doesn't have anything to simplify. Root 16 is 4, and then I would multiply the 3 and the 4 to get 12 root 7. And root 9 is 3, so I'd get 12 root 3. And the square root of 9 is 3, so I'd get 6 root 5. And now I'm going to look for whichever ones have the exact same root, and I can combine their coefficients. Negative 3 and a positive 6 would be 3 root 5 plus 12 root 7 plus 12 root 3, final answer. We already did this example. We haven't done this one yet. This is the square root of 11 divided by 25. Excuse me. I did let you know which property to use when we talked about that quotient property. Remember, it said if you have a divided by b, you can simplify this as root a divided by root b. Well, when I do that with this one, this would just be root 11 divided by root 25. And because we really lucked out and 25 is one of the numbers in our big list, is a perfect square, I can just take the square root of 25 and get root 11 over 5. Final answer. Remember, we can't have a root in our denominator. So in this problem, it worked out nice because we could just take the square root of 25 and get 5, and now we don't have a root in our denominator, and so it would pass all three of those tests. Okay? Root 11 doesn't have any perfect square factors. We don't have a root in our denominator, and we don't have a fraction underneath our root, right? Like we did here. We had a fraction underneath our root. We fixed that already. So we did look out that this number was a perfect square. If this was root 26, this would be a much more complicated problem. It's not, so we're good. But we are going to see problems like that if you didn't guess it. Here we have the square root of 3 over 7. Your first step, you should know, this should be the same as the square root of 3 over the square root of 7. Now we are going to do something very new to us. And it's kind of a trick. So the issue right now is we have a root in our denominator. And we want to simplify that root. We want to not have a root in our denominator anymore. And so what we are going to do is we are going to multiply by 1. And if you were to multiply this by 1, you would get the exact same thing, right? Root 3 over root 7, because multiplying by 1 doesn't change the value of the number. However, we're not actually going to multiply by 1. We're going to multiply by something that's equal to the number 1. So the issue is we have a root 7 in our denominator. What we are going to multiply by is actually root 7 over root 7. How did we pick root 7? That's what's in our denominator. So take whatever is in your denominator and write that over itself, because this is in fact the number 1. Root 7 over root 7, anything divided by itself, is the number 1. So it won't change the value of the number, but it will change how it looks. So what do? Just to reiterate, you take whatever's in the denominator and you write that over itself. Because this is the number 1. It doesn't look necessarily like the number 1, but it is the number 1 because anything divided by itself is 1. Remember how to multiply fractions? You just multiply the numerators across. Root 3 times root 7, using the product property that we talked about today, is root 21. And root 7 times root 7, this is a bit of a trick. Okay? Root 7 times root 7 is the square root of 49. And we know what the square root of 49 is, right? The square root of 49 is 7. So what's the trick that I'm referring to? Well, root 7 times root 7 is 7. Any guess what root 6 times root 6 is? Okay. Root 6 times root 6 is root 36, and the square root of 36 is 6. Okay, this is going to be true for any numbers. If you multiply a root times itself, you can just get rid of the root, take it away. Root 5 times root 5 is 5. Okay, that's going to always be true. So that's why we picked root 7 over root 7 to multiply by in the first place, because I know that that's going to cancel to be 7. Let's do another one. Root 20 over root 11. This is the same as root 20 over root 11. And how do we fix this? Well, actually, there's two issues here, to be honest. One of them is that we have a root in our denominator, root 11, but another one is that 20 has perfect square factors. Yeah? This is the same as root 4 root 5. So I could simplify that numerator as 2 root 5 right away over root 11. It's not necessarily better. You could fix it now or later. It would be the same, but I just fixed it now. Now we are going to multiply by whatever's in the denominator over itself. Root 11 over root 11. Why did we do that? Well, this is just the number 1. And multiplying by 1 is a legal move, right? It's not like we change the value of the number. We just multiply by 1. However, it does make my denominator no longer a root, because I know that root 11 times root 11 is just 11. Up here we have 2 root 5 root 11, and I can just multiply the roots together to get 2 root 55. At this point, I would have to evaluate and make sure that root 55 doesn't have any perfect square factors, and it doesn't. Okay, none of the numbers that are in that big list are factors of 55, so this is the correct answer number. Go ahead and try one more. Root 5 over root 2. Make sure that we get that correct answer. Pause it here, see how you do. That would be root 5 over root 2. And the fancy form of 1, the number that's 1 but doesn't look like it, that you want to multiply by would be root 2 over root 2, which would be root 10 over 2, final answer. So let's look at this example then. We have the square root of 3 over 12. We know, using that property, that we can change this into the square root of 3 divided by the square root of 12. And when we go to simplify this, we have a root in our denominator. We're not allowed to have a root in our denominator. And so what we multiply by is whatever is in our denominator over itself. That way, we're just multiplying by 1. Proceeding here, we know that root 12 times root 12 is just 12, right? That's always true. If you take a root and you multiply it by itself, you can just cancel the root part and take whatever the number is. And when you multiply the numerators, root 3 times root 12, that would just be root 36. We would try to identify if this passes all the tests. It doesn't have a fraction underneath the root like it did originally. It doesn't have a root in our denominator, but the square root of 36 can absolutely be simplified. And actually, root 36 is one of the numbers in the list. It's just 6. So we'd have 6 over 12, which interestingly enough reduces to 1/2. So root 3 over 12 is actually the same as just 1/2. This is going to be a new term for us. I know I'm throwing a ton of material at you guys here, and this is a very long lecture. But we are not done yet, and actually we haven't even done any of the types of problems that it's describing. However, once you know all this stuff, the problems that it's describing in the title are actually quite simple. This is probably the hardest part, though. The conjugate. A math conjugate is formed by changing the sign between two terms in a binomial. For instance, the conjugate of this should go down below. Let's see if I can do that. The conjugate of x plus y is x minus y. Okay, you're changing just the sign in the middle. So the conjugate of 7 plus root 2 would be, hopefully you guys know, 7 minus root 2. And the conjugate of 3 minus root 2 would be 3 plus root 2. We're going to be utilizing conjugates in 4.5 and 4.6 to simplify expressions. It's not exactly easy to do, but work with me here. When you have two terms, a binomial in your denominator, it doesn't work to just multiply by the exact same thing. Like in the last example that we talked about, we had root 12 in our denominator. What did we multiply by? Root 12 over root 12. It doesn't work when you've got two terms in your denominator to do that. Instead, we are still going to multiply by 1, okay, something that is equal to 1. However, it's not going to be the exact same thing. It's going to be the conjugate of the denominator. So 7 minus root 2 over 7 minus root 2. If you guys are thinking strategically here, this is still the number 1. It just doesn't look like 1. And how we choose it is it's going to be the conjugate of your denominator. So what we actually have to do is we have to multiply these things now. And this is going to be a daunting task, maybe perhaps. We're going to distribute the 3 here. In the denominator, we're going to FOIL. So it's a decent amount of work. 3 times 7, right, distributing the 3, that's just 21. And 3 times negative root 2 is just going to be negative 3 root 2. One's in a root, one's not in a root, so you just kind of write them together. You put the one that's not in the root first. 21 minus 3 root 2. Now let's FOIL our denominator. 7 times 7, of course, is just 49. And then we have to do 7 times negative root 2, and we just kind of went over something really similar. You're going to take the one that's in the root and write that first, and then the root after it. So because it's a positive times a negative, it's going to be minus 7 root 2. Right? 7 and root 2 are not like. We can't multiply them other than just writing them together. This one's a positive 7 times root 2, so it's going to be plus 7 root 2. And then we have to do root 2 times negative root 2. Remember, root 2 times root 2 is just going to be 2. It just gets rid of the root. One's positive and one's negative, so it's just going to be minus 2. Multiplying by conjugates is kind of a wild experience because things always happen. Okay? In this problem, we are going to have a minus 7 root 2 and a plus 7 root 2. When you FOIL conjugates, the O and the I were always going to just cancel each other out. This was outside times outside, and this was inside times inside. They just canceled each other out. In 49, and I can just do a minus 2, that's just 47. Our answer here is 21 minus 3 root 2 over 47. Okay, I know that's kind of a wild, like, wait, what? Let's look at it again, see if we can make sense of it. We have a root in our denominator, and we're not allowed to have that. So we need to fix it. We're going to multiply by 1, but it's not going to look like 1. It's going to be the conjugate of the denominator, which is 3 plus root 2 over 3 plus root 2. I have to distribute the numerator, which would be 15. And then 5 times root 2 is just going to be 5 root 2. When it comes to my denominator, this one I have to FOIL. And so I'm going to do 3 times 3 to get 9. 3 times root 2 to get plus 3 root 2. 3 times negative root 2, so it's just going to be minus 3 root 2, right? We're just kind of writing them next to each other and paying attention to the signs, positive or negative. This is a positive number times a negative number, so it's going to be subtract. And then we have negative root 2 times positive root 2. Remember, root 2 times root 2 is just 2, and the negative times a positive is going to be subtract 2. My numerator then would be 15 plus 5 root 2. In my denominator, the O and the I, hey, guess what? They canceled again. And then I just have 9 minus 2, and that's 7. Final answer. Let's do one more of this variety. It would be a great time for, actually, it looks like we got 2 different ones. Let's do them both. It would be a great time to try one, though. This is going to be really similar, except we're going to have to FOIL our numerator and our denominator because it's 2 terms over 2 terms. What are we going to multiply here? 4 minus root 11. And here, 4 minus root 11. This is just the number 1, but it's made up of the conjugate of the denominator. We have to FOIL this numerator. 2 times 4 is 8. 2 times negative root 11 is just going to be minus 2 root 11, right? One's in a root, one's not. Write them next to each other. Pay attention to the signs. This would be plus 4 root 3. And then root 3 times root 11, those ones are both in roots. So we could just write this one as minus root 33. Now we're going to multiply the conjugates by themselves. 4 times 4, of course, is 16. 4 times negative root 11 would be negative 4 root 11. 4 times root 11 would be positive 4 root 11. Guess what? They're going to cancel. And then root 11 times root 11 is just 11. Positive times a negative, it's going to be minus 11. My denominator, the O and the I from FOIL cancel, and we just are left with 16 minus 11, so it's 5. Remember, our goal was to make sure we don't have a root in our denominator, and we have it consistently. It's canceled out, so we don't. As for my numerator, I have one thing that doesn't have a root, one thing that's got a root 11, and root 11 can't be simplified. It doesn't have any perfect square factors. Same thing with root 3, and same thing with root 33. So my numerator, despite how awful it looks, is simplified, 8 minus 2 root 11 plus 4 root 11, 4 root 3 minus root 33, all over 5. I do know for a fact you have a question like that on the test. Let's do one more of this variety. We are going to have to multiply by the conjugate of the denominator, and the conjugate of the denominator would be 9 minus root 7 over 9 minus root 7. We're going to have to do negative 1 times both of those. Negative 1 just changes the sign, right? Negative 1 times negative, or negative 1 times 9 is negative 9. And negative 1 times negative root 7, negative times a negative is positive, and 1 times root 7 is just root 7. Now let's go ahead and FOIL out the denominator. 9 times 9 is 81. 9 times negative root 7 is minus 9 root 7. Root 7 times 9 would be positive 9 root 7. And then root 7 times negative root 7 would just be minus 7. Those canceled. We just have negative 9 plus root 7 over 81 minus 7, which would be 74. We did a lot of those examples. Hopefully that is starting to make sense to you. And I'm going to go ahead and pause it here and start here for the next lecture. This is still section 4.5, and I know it's a lot, but now we're actually going to start solving equations. All of that part was just simplifying the square root signs. But when it comes to solving the equations, if you're really good at simplifying the roots, this part will be fairly straightforward. So let me know if any questions you have, and make sure to watch part B.